Hi guys, you're welcome back to God Academy, and in this session I'm going to take you through applications of differentials. In our previous lessons we've gone through the foundation and we built it up, and in our immediate last session we went through the partial derivatives. Then we moved forward doing the total derivatives, right? Total derivatives. Then we climbed up, then we did the chain rule, and everything about differentials. So at this point, it's assumed that all of you understand differentials of multivariable function, or you say calculus with several variables. So the differentiation of functions involving several variables. But in the course of calculus, anytime you do differentiation, you need to do the application because it's the relevance of the mathematics that makes it so important, right? So therefore, how do we apply differentials, particularly in functions with several variables? For you to appreciate this. Okay. So in this lesson, we're going to do applications of differentials, and we have several applications we're going to touch on and see how to approach any problem of a sort. The first one we are going to talk about is what we call directional derivative. Directional derivatives. Okay. So at this point, if you have not subscribed to this channel, please do well to subscribe, and also make sure you share to your friends who haven't got to know about this program so that they joined as well. And make sure you stick to the video and watch till the end. If you haven't watched any of the previous editions too, for you to understand this better and to save you from the stress of you not understanding things at the later time, please do well to visit all the previous videos and you move along smoothly. So applications of differentials, as I said, directional derivatives. So this is actually not anything new, but we are just moving to a different dimension. We've done directional derivatives in calculus 1. So now you're going to do directional derivatives in calculus with multiple variables. Okay. So we are going to deal with the rate of change of some quantities, and finding the maximum and the minimum and all that is still the same thing. It doesn't change, but the algorithm behaves differently. Okay. Okay, so now generally, if you want to solve for directional derivatives, let me write the formulas here so that we appreciate it a while. Okay. So the directional derivative represented as d, okay, sub u, where u is a directional vector, okay, of a function of x and y is given as the the partial derivative with respect to x of xy multiplying a plus the partial derivative with respect to y of xy multiplying b, where a and b are your direction numbers. Okay, so your a and b are simply the direction numbers of the vector u. This is for two variables, right? So you can do similar for three variable where you have f of x, y, z. It happens that you have fx of x, y, z multiplying a plus fy of x, y, z multiplying b plus a function of z, that is the partial derivative with respect to z, since it's three variables, of x, y, z times c. So here you realize that your vector is going to be three variables, right? Three variables. You have A, B, and C like this. So that's the idea. So simply, we are just trying to relate the rate of change of our function with respect to a certain point. Okay, you'll be solving a couple of examples for you to understand it very well. So you understand that calculus is all about understanding the rate of change, how a function is changing. Okay, how a function is changing. That is the whole concept of what calculus, right? So now this is what you are going to do. Assuming that you are standing on a hill, right? You are standing on a hill. Let me use some light illustration. So let's say we have a hill right now. Okay, let's say there is a hill and you are standing somewhere away from the hill, right? So when you talk about directional derivative, okay, it's about how, let's say you want to approach or move to a certain point. Okay, there are so many different directions which you are going to take. So directional derivative is about the changing effect of a function with respect to a certain point. So looking at the point where we are, let's say we are at a point xy. Okay, you want to find the shortest. So for you to always use the directional derivative, you will know the function. Okay, let's say for you to move from here to where you are, it is expressed as a function. Let's say f of xy is given by what? Let's say ax plus something something. Okay, so once you express the whole direction with a function, then you realize that anytime you differentiate a function, you get what you call um when you differentiate a function, I mean the first derivative, right? That's a gradient function. You realize that you can find the maximum rate of change. Okay, the maximum rate of change. But since this one is a multiple variable, you realize that the change of x may not be the same as what the change of y. Okay, so here we use what we call the vector. We have the vector here, which vector um which gives a direction of where exactly you want to apply the change. Okay, so you may not appreciate it here. So let's solve a couple of examples for you to understand. So how to move along a changing function is what you are doing. Okay. So let's see an example here. I have my example first one, which is du, right? When you see this notation, that is, you should think about directional derivatives, okay, of a function 2, 0, where f of xy is equal to x multiplying e to the power xy plus y. And the unit vector or the directional vector, okay, is the unit vector in the direction of theta is equal to 2 pi on 3. Theta is equal to 2 pi on 3. So it says that we have a directional derivative of a point 2, 0 where the function is given as what? X multiplying e to the power xy plus y. And our directional vector is the unit vector in the direction of theta is equal to 2 pi over 3. So the idea, as I said, behind directional derivative is that we are going to move along a changing function being directed by a certain vector. That is all. So it's simply the dot product of a gradient function and a particular vector. That is all. The dot product of a gradient function and a vector. Okay, so the gradient function is represented as inverted this. So when you see any inverted triangle attached to f, it means the gradient function dots the u. Okay, so here you can see it's a dot product, the dot product. That is why the formula here, you realize that you have a is multiplying the gradient function with respect to x, b, so the directional numbers multiplies each and add. That is dot product. So how do you solve this problem? Whenever they give you any directional derivative problem to solve, okay, you only need two things. You need your function and you need your what? Your direction vector. The direction vector may not always be given directly, okay? It may sometimes be given in the form of an angle, okay? So he said that our direction vector is what? Is the unit vector in the direction of this. So here it has already stated that it's a unit vector. So there's no need for us to what? Find the unit vector in that direction again. So mostly we try to make the vector become what? Has a magnitude of 1 so that it doesn't affect the weight of our changing function. But since they've mentioned a unit vector in this problem, we are simply going to use our angle straight away. You will see the next problem if they don't say unit vector, how it's being solved. Okay. So here you first write your function down. Okay. That's the first thing. Our function f of xy is given as what? X multiplying e to the power xy plus y. Is that not it? Then once you have your function down, you move to your what? Your u. Our u is saying that, so it's a vector. So don't forget your angle brackets. Then it's saying that it's a unit vector in the direction of this. Please, whenever they give you theta and you want to find the respective component, you use cosine and sine. Okay. So cosine and unit vector, we don't have any r. Remember from algebra. So cosine of the expression 2 pi on 3, right? We can choose to add I and J, but comma sine of the expression 2 pi on 3, like this. Then you simplify. So our u will be given as what? If you have this cosine of the expression 2 pi on 3, we are going to have the angles to be negative half. Then let me punch this here. So we have 2 pi on 3, which um so that is 120, right? So you have cos 120 and sine 120. So cos 120 is obviously negative half as you've written. Then sine 120 is given as root 3 out of 2. Okay, root 3 out of 2. Then you close it. So now I have my u. But my function, I need my gradient function. So here I'll break it. You need fx and fy. Okay. So our derivative with respect to x, what are you going to get? If you're differentiating this expression with respect to x, remember that if you're differentiating this expression with respect to x, any y term becomes what? A constant. Don't forget that. We did that in partial derivative. Anytime you are differentiating an expression, which is a multivariable function, with respect to one of its variables, you end up getting the other variable being a constant at that instant. Okay, becomes a constant at that instant. So how do we simplify this? Remember that if you want to differentiate with respect to x, y here becomes what? A constant. Okay, so here it becomes what? 0. But this expression here, since we want to differentiate with respect to x, it becomes what do we say, the product true, because this one, it confuses a lot of people. When you have this one is a linear function, this is an exponential function, and each of them has got x. So if you want to differentiate, you cannot use a normal exponential. Don't be tricked that this is an exponential, the whole thing is exponential function, so we just multiply anything. No, we have x here, we have x at the power. So the two of them are two different types of function carrying the same variable we are going to differentiate. So it becomes product true. So what do we do then? You first differentiate your x whilst maintaining this. Okay. So when I differentiate my x, I get 1 multiplying e to the power xy plus. Now I'll maintain this and differentiate this with respect to x. That will give me y e to the power what? This. So that will give me what? Xy e to the power xy nicely. Here will be plus what? 0 because y is a constant. Therefore, my fx is simply e to the power xy plus xy e to the power xy. Okay. Now you find your fy. Your fy here. How do you differentiate this with respect to y? With respect to y, x is a constant. So here now is just an exponential function, only one exponential function. So if you want to differentiate this with respect to y, you get y when you differentiate here, since it's a product, you differentiate the yx here, and whatever you get will come and multiply the whole function. Okay, it will come and multiply the whole function. So you end up getting x squared, because here when you differentiate this, it will come and multiply. So x squared e to the power xy. Then here when you differentiate y, you get what? 1 nicely. So this is the first step. Now we have our partial derivatives ready. Okay. But remember that our partial derivatives that we are looking for, we want to find the partial derivative at a point given as 2, 0. At 2, 0. Okay. So at point 2, 0. So here let's find fx of xy. But now becomes fx of 2 comma 0. So what's the answer? Wherever I see x, I put 2. Wherever I see y, I put 0. I'll get e to the power 2 times 0 plus my x 2 times 0 times e to the power 2 times 0. Obviously, this is 1. Then this goes to 0 because 0 is multiplying the entire thing. So this gives me what? 1, right? Good. So I have here to be 1. Then when I come to this side too, I have my fy. Then fy of 2, 0. I'll end up getting 2 squared multiplying e to the power 2 times 0 plus 1, right? This gives me 4 because this is 1 plus 1, and that is equal to what? 5. So I have my fx of 20 to be what? 1, and the fy of 20 to be 5. Now that we've gotten our partial derivatives and the functional values there, we simply have to do our cross product and we are done. Okay. So we simply have to do our cross product. So therefore, I'll simply have, let's go back to the formula and see. So the formula is saying that you simply multiply your fx where you have put the functional value inside times the first directional number plus fy times the second directional number. So that's what you're going to do. Okay. So you say that our um so our let me do it this way. Our gradient function f dot u is going to be equal to, our gradient function is giving us 1 comma 5 dot our u is what? Negative half comma what? Root 3 on 2. Therefore, this becomes 1 times negative half plus 5 times root 3 on 2. And this gives negative half plus 5 root 3 on 2, giving us 5 root 3 minus 1 all over 2 as the answer for our directional derivatives. And this is how we solve this. Okay, it's not difficult. This is how we solve these problems. Okay, anytime you see these problems, make sure you go through the same approach. Okay, anytime you encounter this, make sure you go through the same. Now let's solve another problem, make things clearer. So our example 2, the question says that um okay, so now we have du of f x y z. So now there's 3 variables. Okay, is you should find this. Okay, so the problem says you should find this where f of x y z is given as s squared z plus y cubed squared minus x y. My vector is given as negative 1 0 3. Okay, nicely. So here in this problem, we realize that they've given us our vector, but it is not the unit vector in that direction. So see, the explanation is this. We want to only use the direction of the vector. We are interested in the direction the vector is telling us. We don't need its magnitude. So you have to make sure you convert it to a unit vector. Unless the question says that the unit vector is this and that. That's where you see that, oh, initially the question has already stated. So you use the vector directly. If the question doesn't state as a unit vector, please don't use a vector directly. Otherwise, the weight, that is the magnitude of the vector, will affect our partial derivatives. Good. So at this point, what do? We find our fx, fy, then fz. Okay. Then you put the functional value. But here, we aren't given any functional value. So our answer will be in terms of what? X, Y, Z. Okay. So our fx will be what? 2xz. This becomes 0 plus 0 minus yz, giving us 2xz minus yz as the answer. Our fy is going to give us, differentiating with respect to y is 0, plus 3y squared is z squared. Differentiating this with respect to y is minus xz. Good. So the answer is simply 3y squared z squared minus x. Then finally fz, you get x squared plus 2y cubed z, then minus what? Xy. Good. At this point, what do? We take our dot product, as simple as that. So our gradient vector now is given as a vector where I have 2xz minus yz, comma 3y squared z squared minus xz, comma x squared plus 2y cubed z minus xy angle dots. Now let's convert this one. So here, that's where you're going to convert this to a unit vector. Converting it to a unit vector, we simply have to do what? We take the square root, we find the length of our vector. So square root of -1 squared plus 0 squared plus 3 squared. This gives us square root of 10. You know this, okay? So our unit vector becomes 1 over square root of 10 times -1, 0, 3, which is the same as -1 over root 10, comma 0 over root 10 is 0, comma 3 over root 10. As simple as that. So I have -1 over root 10 here, comma 0, comma 3 root 10, like this. At this point, my solution becomes 2xz minus, so 2xz minus yz times -1 over root 10. Then you realize that this becomes 0. The second one will become 0, so I wouldn't even add a plus. X squared plus 2y cubed z minus xy times 3 on root 10. And that will give us our answer. I can factorize 1 over root 10 out. 1 over root 10 outside, then -2xz plus yz. Then I have plus 3 times, so 3x squared plus 6y cubed z minus 3xy. So can we simplify this further? We have xz. We have xz. No. We have yz. We have yz. Okay. I think we can do something about that. Then xy. Okay. So we simply have to maintain 3x squared minus 2xz plus 7. No, this is y cubed z. So let's still have yz plus 6y cubed. And I don't know if I've, yeah, minus 3xy. But that's the whole explanation, okay? 1 over root 10. And this gives you your directional derivative. Okay, as simple as that. Your gradient functions dots your directional vector, where your directional vector is a unit vector. Please take note of that. Let's talk about this theorem here and one beautiful application of directional derivatives. So there is a theorem. It says that the maximum value, right? The maximum value of du f of x, right? Which is the change, the maximum rate of change of the function f of x, right? Is given by the length of this. Okay. So it's saying that the maximum value of our directional derivative is given by, so is given by this expression. So whenever you find your directional derivatives and you take the length of your directional derivative, you end up getting the maximum value of it. Okay. And he said that it will occur in the direction given by our directional derivative. So let's see something here. Remember that, as I said, you have the gradient function. The whole idea of directional derivative is to have my gradient function, which in this case you have fx, fy, fz as a vector, right? Dots my u, which is my directional vector. You remember from algebra that anytime you have two vectors, which are, the dot product of any two vectors is giving us the absolute length of what each vector dots, like this, right? So this is time, sorry, not dots, times this cos theta. Now, for us to find the maximum value of any of our directional derivatives, there's one thing that should happen. The angle here should be what? Zero. That's it. Therefore, cos theta should be what? Zero. Right? Sorry. Therefore, the angle here should be 1. For the maximum value, the angle here should be 1. Therefore, theta should be 0. Okay. So cos theta should be equal to 1. Therefore, theta should be 0. What this means that for you to have the maximum value for our directional derivative means that the direction of our vector should be in parallel with the change of our function. It should be rightly parallel. Get the maximum. Okay, so let's solve a problem on this. The word problem actually. Good. So this is a problem. It says suppose that the height of a hill above sea level is given by d is equal to 1000 minus 0.01 x squared minus 0.02 y squared. If you are at the point 60, 100, in what direction is the elevation changing fastest? What is the maximum rate of change of the elevation at this point? Good. So it says that suppose that the height of a hill above sea level is given by the function z is equal to 1000 minus 0.0 x squared minus 0.02 y squared. If you are at the point 60, 100, okay, imagine in what direction is the elevation changing fastest and what is the maximum rate of change of the elevation at this point. So this is where the idea of directional derivatives in calculus comes here. So this thing that you have here is a quadratic surface. Z is equal to 1000 minus this. This is a quadratic surface, okay? So we are trying to find the direction in which our elevation is changing fastest, okay? So there is a hill here. It's saying that this hill is above the sea level and is given by this equation defined. So let's assume that it's a cone, right? So let's assume that it's a cone. So with this hill here, okay, with this hill here, you realize that he said if you're at a point 60, 100, in what direction is the elevation changing fastest? Our current point xy maps towards 60, 100. To know the direction that the elevation will change fastest, what do? We need to differentiate define the gradient function of the model. So here you see the height has been modeled as a function of xy. So you need to differentiate this. And at the point which is at the gradient function, you then apply the necessary condition. Okay, so the first thing to do is first let's extract our gradient, our function 1000 minus 0.01 squared minus 0.02 y squared. Then we find our gradient function. Our gradient function is going to be our this. So here, you are going to get it in two parts, right? You get for fx and what fy. Okay. So for our fx, what are you getting for fx? Or together, all together, let's add all of them together. Differentiating this with respect to x, 1000 will be 0. I'll get negative 0.02 x. This will be what? 0. Comma, let me differentiate with respect to y and add it. This will be 0, this will be 0, this becomes what? Negative 0.04 y. Nicely. So these two then becomes our gradient function. Which point are we? So then our gradient function at the point 60, 100 is going to give us what? You multiply. So you see that this is x, this is y. At the point 60, 100, wherever you see x, you put what? Or 60, wherever you see y, you put your what? 100. Therefore, we are going to get an expression of what? Negative 1.2, comma, negative 4. Nicely done. Okay. Then we are looking for the point where you have um so this is the point where it's gonna occur. Okay, so our maximum, the greatest rate of change, will occur at this point. Please take note. It will occur at this point. This is where it will occur. When you find your gradient function and you put the point where you are standing, okay, it will give you the point which, I don't know if you are appreciating that. You see, whenever you differentiate your function, okay, and you get your gradient function, that gradient function is a very powerful function, okay, used for optimization. And they are asking you that in what direction is elevation changing fastest? And that direction is the vector which depends on where you were standing. And where you were standing is what 60, 100. So when you multiply your vector, that is like the dot product, okay, by your gradient function, you end up getting the point where your changing will be what fastest. Then you find what is the maximum rate of change. That was the second part. Then what is the maximum rate of change? According to the theorem I explained, the maximum rate of change will simply be equal to what? The absolute of our what? Maximum gradient function. Like this, the absolute of this expression. So what do we get? Square root of what? Negative 1.2 all squared plus negative 4 squared. And you are going to get 4.176. Simple. Good. So you can say that currently you are standing at point 60, 100, and the point where our elevation will be changing fastest will be at negative 1.2, negative 4. Then you have your maximum rate of change to be equal to 4.176. As simple as that. Okay, let's move to the second subtopic. So the second subtopic, we have what we call tangent planes. Tangent planes and linear approximation. These are all powerful applications of differentials. So tangent planes and linear approximation. Now, let me write some of the formulas that you need to know here before we start. Okay. So, to find the equation of a tangent plane in differentials, we say that z minus z naught is equal to the fx, which is the partial derivative with respect to x of x naught y naught multiplying x minus x naught. Please, this is not any plenty formula. Plus fy of x naught y naught multiplying y minus y naught. As simple as that. As simple as that. So here, what you are trying to say is, you remember that whenever you want to find the equation of a plane, you need a direction, right? So way back in algebra, you need what you call the normal vector. Here, the normal vector which you are going to use are partial derivatives. Okay. Given a function where z is equal to f of xy, you realize that the z naught here then becomes what? F of x naught y naught. Okay. Which you also put inside the equation. So in some cases, you see f of x naught y naught as part of it instead of minus z naught. Okay. That is how it is done. So how do we apply these formulas and how do we appreciate this application? They'll give you a particular question. Let's solve one problem here. We said that find the equation of the tangent plane to z is equal to natural log of 2x plus y at the point -1, 3. Find the equation of the tangent plane to this curve at the point -1, 3. That's the kind of question you'll be given. Okay? So you ask yourself, how do I find the equation of a tangent plane to a curve at a point? The only thing that you should appreciate is you um finding your gradient function. Okay, the gradient function is our central idea here. Okay, you realize that you need the direction numbers in that your plane is only going to get a direction from this vector. The vector will help us get the direction of the plane. Okay, and that will help us define the equation of the plane at this point. As simple as that. And what will be the direction? The direction is simply what? Finding fx at -1, 3 and finding fy at -1, 3. Once you get these two values, then it means that we're actually done, right? It means that we are actually what? Done. Okay. So this is what we do. So our equation then, as we said, we are simply going to have, let's do it this way. So from the main equation I've written, good. So here you realize that at this point, you are going to find fx and fy. Let's find it. Fx is what? When you differentiate this with respect to x, meaning that y will be a constant, okay? And this one is a natural log. Anytime you want to differentiate a natural log, you differentiate what is inside the argument over itself. I say it again. When you differentiate, so typical, let's say ln x. If you want to differentiate ln x, what do you get? You get 1 over x. Why? You differentiate the x itself, you get 1 over itself. So here you differentiate the factor here over the whole expression back again. Okay. So when you differentiate 2x plus y, now you want to differentiate with respect to x, meaning y is a constant. So that will give me 2. Okay. So my fx -1, 3 will give me, let me make it fx of xy. Fx of xy will give me 2 over 2x plus y. Okay. Then my fx of negative 1, 3. But negative, so I have 2 over 2 times negative 1 plus 3. And this is what? 2. So this is negative 2 plus 0. When I come to my fy of xy, I'll get here when you differentiate y, you get 1. So 1 over the same expression 2x plus y. For the differentiation part, nobody will teach you. You've done it already, so you should be able to find the derivative of this expression in first. So this one is just application of first calculus 1. Okay. So it's progressive. So at this point, you find your fy of negative 1 comma 3. Like that, you're going to get 1 over the expression 2 multiplying negative 1 plus 3. That's going to give us 1. So now we have fx2, fy1, right? Good. Then you realize that we needed what? Our z naught, which is what? Z naught, which is f of x naught. So our z naught is equal to f of what? X naught, y naught, so f of negative 1, 3. You put this one directly. So z becomes what? Natural log of what? 2 times negative 1 plus what? Um, 3. This is negative 2, 1. Len 1, what's the answer for len 1? Len 1 is 0. So this gives us z equal to 0. Therefore, we have z or z minus 0 is equal to, we have this one, our fx give us what? Open bracket x minus x naught plus our y give us what? 1. Y minus what? Y naught. So our z is equal to 2 minus x. Our x naught is negative 1 plus 1 plus 1. Y naught is what? 3, right? And it's also, you get z is equal to 2x plus 2 plus y minus 3. This is 2x plus y minus equal to z. And this is the equation of the plane, which is tangent to the curve at that point. As simple as that. So it's so simple that you only have to find your gradient function at that point. Then you do the necessary. As now, let's do a bit of linear approximation. So for linear approximation, is an algorithm which you use to approximate rate of change, provided the point you're approaching is very, very close. Okay. So generally, linear approximation is said to be linear approximation of at a point xy simply equal to the functional value at a point x naught y naught plus fx s naught y naught multiplying x minus x naught plus fy multiplying x naught y naught multiplying y minus y naught. So you realize that this is almost the same as the equation of a plane to of a tangent plane towards a curve, right? So it's almost the same thing. So you simply have to follow the formula. Okay. The idea is that you definitely know that given any function of xy at a point, you are saying that the linear approximation is that we assume that this whole change is small and doesn't affect our value so much. This is actually the value. Okay? This is actually the value with the smallest change. So this particular type was when way back in high school we find 5 square root of 5.00. For you to find this value without using a calculator, use linear approximation, where the change will factor what the 0.001 aspect, then the 5 will be there. That is the whole idea. I don't know if you're appreciating it, but so then let's solve a problem. So given a function of xy equal to 3 plus x squared over 6 plus y squared over 9. Okay, we are to find the linear approximation. Okay, at negative 4, 3. At negative 4, 3. So we have our point to be negative 4, 3. So we should find the linear approximation at this particular point. So what do you need? Looking at the formula, the first thing that we actually even need is you finding your functional value. So you put in this directly. So what do you get? F of what? Negative 4 and 3 is equal to what? 3 plus. When I put negative 4 here, I get 16 over 6. Plus when I put 3 here, I'll get what? 9 over 9. This gives me 3 plus 1, which is 5. So I simply have 5 plus my partial derivative with respect to x, partial derivative with respect to x. Okay, it's simply going to give me, so what's this with respect to x? Realize that this becomes 0. So let's find that one separately. So our fx of xy is going to give us, it should be 0 plus, it should be what? 2 times this. So we get x over 8. This becomes 0, right? So if you have x over 8, then our fx of negative 4 comma 3 will be equal to what? You simply have to put your x here, right? And that is what? Negative half, right? So here we get negative half multiplying x minus x naught. The same for our fy of xy. When you differentiate this with respect to y, this will be 0, this will be 0. So you have 0 plus 0. And here will be becoming 2 over 9y. 2 over 9y, right? So 2 over 9y. Then you put in your point at, so your fy at negative 4, 3 be equal to 2 over 9 times 3. That is going to give us what? 2 over 3. So we have here to be plus 2 over 3 multiplying y minus what? 3. So we have to substitute. So let's simplify. So we simply have 5 minus 1 out of 2 multiplying x. Our x naught is what? Is 4. So plus 4, right? So our linear approximation at the point negative 4, 3 equals 5 minus 1 out of 2 multiplying x plus 4. Okay. Then plus 2 out of 3 multiplying y minus 3. So that's good. So this is the whole idea. This is whole idea. Okay, good. This is all for linear approximation, and let's proceed. Good. So I have tangent tangent planes, okay, and normal lines. So let's treat this one as a whole again. Okay. So tangent planes, and we have normal lines. Here, as I said, the whole concept of tangent planes, application of differentials is the fact that it gives us what we call gradient vector. This gradient vector is actually the same normal vector we know. It's the same directional vector we know anytime. So our gradient vector f is given as fx, fy, fz. Once you have this, you are done, because we have already done a revision on equations of planes and lines. As simple as that. This is only the difference in this application stuff we are doing. Okay. So therefore, the tangent plane formula, let me write the formulas for you. So tangent plane formula is given as You have f, so this is in three dimension, okay? You have f x of x naught, y naught, z naught, multiplying x minus x naught. You have plus f y x naught, y naught, z naught, multiplying y minus y naught, okay? Plus f z x naught, y naught, z naught, multiplying z minus z naught is equal to 0. This is simply the tangent plane equation. Our fx, fy, fz is simply the gradient vector, as simple as that. Okay. Then the normal line equation for the normal line. So it seems I'm just giving you formulas for you to chew, right? Yes. So the more you solve more problems, the more you get it. But here I'm just opening your eyes, different things that you need, different formulas that will help you solve most of the problems. So with the normal line, you're going to have the vector r of t. So this one is the, you remember parametric equations, right? So vector equations of a line is going to be given by the vector x naught, y naught, z naught plus t multiplying what? The gradient vector of x naught, y naught, z naught. I hope you get this. So remember that in finding the equation of a line in 3D, as we did, to find the parametric equation, we need what you call the vector, okay? A parallel vector in space. Here we need our gradient vector, as simple as that at that point. Okay, so let's solve this problem. Find the tangent plane and normal line to the function x squared plus y squared plus z squared is equal to 30 at the point 1, -2, 5, like this. To find the tangent plane and the normal line to this. So this is something like a sphere, right? Something like a sphere at the point 1, -2, and 5. What do we do? Straight away, you don't need to think plenty. What is your vector? Sorry, gradient vector. It's simply going to be a function of what? Fx, Fy, and Fz. Our function here is what? Our function of x, y, z is given as what? X squared plus y squared plus z squared. Therefore, our gradient vector is so simple. 2x, 2y, 2z for each of them. That is all. So once you have this gradient vector, then what do we need? Need a gradient vector at the point 1, -2, then 5. That is going to give us 1, 2 times 1, 2, 2 times -2, -4, 2 times 5 is what? 10, like this. So 2, -4, 10 is what we have. Then we find the tangent plane. So once you have this, you're almost good to go, right? So 2 is our fx. So our fx is 2 multiplied by what? X minus x naught. And our x naught is what? 1. Our fy is what? Minus 4 multiplying y minus y naught, which is what? -2. So plus 2. Plus our z naught, which is 10, right? So 10 multiplying z minus what? 5 is equal to 0. Simplify this and you are good to go. So here this gives us 2x minus 2 minus 4y minus 4z plus 10z minus 50, sorry, for 0. So 2x minus 4y plus 10 minus 2, right? Oh, sorry, this one was plus 2, so minus 8. So minus 2 minus 8 minus 10 minus 60, okay, equal to 6. Here you can divide through x minus y plus 5z plus um coach. I repeat. plus 5z is equal to 10. Good. Simple as that. Now the next thing is to find a normal line. The next thing is to find a normal line. So the equation for the normal line is what? The vector RT is equal to, as I said, we have our known point R naught plus T multiplying our gradient function. What's our known point? Our known point is simply what? 1, -2, 5, right? Plus T multiplying our gradient vector at that point, which is 2, -4, 10. So here what do you have? Our vector equation equals 1 plus 2t, -2 plus what? -4t, 5 plus 10. And that is all for this. So this is how we deal with directional derivative, finding tangent, equation of normal. It's not difficult. You need your functional, your gradient vector, your gradient function at that point, then you go your way. Let's touch on the last part, which we call relative minimum and maximum. Relative minimum and maximum. This one is very technical, so relative minimum, maximum. Good. Relative minimum and maximum. So relative minimum and maximum is something you know. Remember that in calculus with single variable, if I draw a curve and I do something like this, we have this to be our global minimum, we have a local minimum, we have a local maximum, we have a global maximum. Remember exactly what you are going to do here again. So here I won't talk plenty since you have an idea of, we need some few things. We need one, what you call the critical point. Critical point. Is that not it? You remember what you call the maximum point. We have what you call the minimum point. We have what you call the saddle point or point of inflection. Point of inflection, right? Now, these are things that you know already. So because of that, let's move straight into the multivariable part of it. There is a new term I'm going to call here determiner. A determiner. Interestingly, if you have a multivariable function, okay, and you find your critical point, it's not easy for you to test that the function is maximum at that point or minimum at that point. So we have what you call a determiner, and the determiner helps us to determine whether a function is minimum or maximum. And you have to chew this algorithm in your mind, okay? Now, what's the determiner? The determiner D at a point AB is given as fxx. You remember fxx? Yes, you should remember. Of AB multiplying fyy of AB minus the expression fxy multiplying AB all squared. Sorry, good. This is the determiner. When you multiply your second derivative of the x and the y side and you subtract it from this second derivative of, the opposite, all squared, you get what you call a determiner D. What do we use D for? D is used for testing whether a point will be saddle point, minimum or maximum point. Okay. So now these are the algorithm. One, if D is greater than 0 and fxx at point AB is greater than 0, then there is relative maximum. Oh, sorry, relative minimum at point AB. If D is greater than 0 and fxx of AB is less than 0, then there is relative maximum. If D is less than 0 Then there is points of inflection, or what you call the saddle point. Saddle point. Then you can get d to be equal to 0. We call it indeterminate. Don't You can't determine it whether it is maximum or minimum. So please, these are the algorithm we'll be using right now to solve our problem. So straight away, let's solve a nice problem here without talking plenty. We're going to have find and classify. So find and classify all the critical points of the function of xy is equal to 4 plus s cubed plus y cubed minus 3xy. Find and classify all the critical points of f of xy given as 4 plus x cubed plus y cubed minus 3xy. Solution. Okay. Find and classify all the critical points of f of xy is equal to 4 plus s cubed plus y cubed minus 8. Now, the first thing to do is to know your critical point. Is that not it? But to know your critical point, you need your first derivative, right? So we need what you call the fx and the fy. That's the first step, okay? So here's our function, f of xy giving us 4 plus s cubed plus y cubed minus 3xy, okay? So this that we have here, we need the fx. What's the fx? The first derivative, this will be 0, this will be 3x squared, this will be 0, and this will be what? Minus 3y. So our first derivative fx is giving us 3x squared minus 3y. Our fy is going to give us what? 0 plus 0 plus 3y squared minus 3x, giving us 3y squared minus 3x. These are our first derivative. And we know critical point is just equating the y over the s to 0. So we equate this to 0, we equate this to 0 to find the critical point. These are two nonlinear equations for us to solve. From the first equation, 3x squared is equal to 3y. Therefore, we can say y, 3 will cancel 3. So y is equal to x squared. And put this into the what? Equation, this equation. Okay. When I put this into this equation, wherever I see y, I'll put what? X squared. I have 3, open bracket, x squared all squared minus 3x equals 0. This gives 3x to the power 4 minus 3x equals 0. Factorizing 3x out, I have x cubed minus 1 equals 0. Is that not it? So therefore, at this point, I can say that x is either equal to 0 or x is equal to what? 1. Now, you know that y is equal to what? S squared. So when x is equal to 0, y will be what? Y will be 0. When x is equal to 1, y will be what? 1. Therefore, our critical point is 0, 0, 1, 1. We have identified our critical point. Is that not it? Good. Once you find our critical point, the next thing to do is to find our fxx, fxx, and fyy, then fxy. These stuffs are we know. The second derivative. You know, initially, second derivative from our single variable is just 1, but here is 3 possibilities: fxs, fyy, fxy. Actually, we should have added fyx, but sake of Clorus theorem, which say that whatever you are doing with a continuous function, your fxy and your fyx is always the same. So at this point, what do? You have your fxs, fyy. We need to find our d, the determiner, so that we know whether this critical point is either maximum or minimum. Likewise, this one too. So our determiner is saying that we are going to have this fxs at the particular point which we are dealing with, okay, and fyy. Good. Okay. What is fxs? What is fxs? So here's my fx. My fx gave me what? 3y, a 3x squared minus 0y. This is my fx, right? When I differentiate this, what am I getting? I'm going to get 6x. When I differentiate it, what am I going to get? I'm going to get 6y. Okay, these are my fx's and fyy. Okay, so I'm going to get 6x times 6y minus, then what is my fxy? Fxy, you can use fx1, right? So here I'm going to differentiate it with respect to y. This will be 0. I have negative 3. So minus what? 3 squared, right? So minus 3 squared. And that will give me my. So this gives me 36xy minus what? 9. Okay. Then we put the point. So at that point, you want to find our determinant. So this is the first one. When you want to test for critical point 0, 0, you put 0, 0 here, and that will give us what? Negative 9. So our determinant at 0, 0 is giving us what? Negative 9, and that is less than what? 0. So we go back to our algorithm. When the determinant is less than 0, what does it mean? It means that there is point of inflection or it's a saddle point. Then we conclude that the critical point 0, 0 is a saddle point, as simple as possible. Then we move to D at 1, 1. What do you get? 36 times 1 times 1 minus 9, right? That's going to give us 36 minus 9, giving us what? Um, 27, right? And that is greater than what? 0. Is that not it? If 27 is greater than 0, then you know that when D is greater than 0, there are two possibilities. We still then go to fxx at that point. If the fxx at that point is less than or greater than 0, we can confirm. The fxx is what? 6x. And what is my point? My point is what? 1, 1. So when I put 1, I get 6. And 6 is obviously greater than 0. That's not it. Therefore, you have what? A relative minimum point. So therefore, since fxx at 1, 1 is equal to 6 and is greater than 0, you say that the point 1, 1, the critical point 1, 1 is a relative minimum. So this is how we find relative minimum, global minimum first variable function. We use the determinant D. And please solve more problems so that you understand. Thank you for joining us for this session. See you in the next session. Don't forget to subscribe.